And it's a little bit of a strange word, but what it takes a look at are the physical properties of the solvent that are affected because of the presence of a dissolved solute. The dissolved solute interferes with the attractions between the solvent molecules. So our primary solvent, or the only one we really look at, is water. So when we dissolve something like a salt or a sugar in water, those particles interfere with the water-to-water attractions. And the two properties that we really take a look at is how does that dissolved solute affect the boiling point of water and the freezing point of water. So let's take a look right here. So 100 degrees Celsius. This is what we recognize as the boiling point of pure water. So if you ask any chemistry student what's the boiling point of water, they're going to say 100 degrees Celsius. Versus 0 degrees Celsius, we recognize this as the freezing point of pure water. So now, what happens to the boiling point of water when it's part of an aqueous solution? Well, it's called boiling point elevation. So what that means is that the solution's boiling point will be higher or greater than the pure solvent's boiling point. So that means that if we have an aqueous solution, the aqueous solution is the boiling point of our aqueous solution is higher than pure waters. So it's called boiling point elevation. So I like to write the B with a little arrow up at the top. So the boiling point of our aqueous solution is going to be greater than 100 degrees Celsius. Whereas the freezing point, it's referred to as the freezing point depression because the solution's freezing point will be lower, will occur at a lower temperature than the pure solvent. So if pure water freezes at 0 degrees Celsius, we will have a negative temperature, a temperature below 0 for our freezing point. So we have a freezing point. I like to make the F with a little down arrow. So the freezing point of our aqueous solution will be less than 0 degrees Celsius. It'll be a negative temperature. So boiling point elevation, we go above the solvent's normal boiling point. Freezing point depression, the solution freezes at a temperature lower than the normal freezing point. So using those ideas, you have to apply them to the solvents. So we have 3 questions to take a look at, okay? And so it asks which solute will change water's boiling point and freezing point the most. So if it elevates the boiling point, then it also depresses or lowers the freezing point. So when we take a look here at our 3 possibilities, we notice we have M, so that's molarity concentration, that all 3 possibilities have the same molarity. Okay, so if they have the same molarity, we know that they are dissolved because they are all aqueous. We understand that they are dissolved and in solution, but then we take a look at the chemical formulas. So they have the same molarities, but they are classified as different substances. So see, this solute is made up of carbon, hydrogen, and oxygen, so it's all nonmetals, which means it's a molecule. NaCl, Na is a metal, Cl is a nonmetal, so we have a metal plus a nonmetal. So here we have something that is ionic. And then lastly, our last substance, it's made up of only oxygen atoms. So all the atoms present are nonmetals. So we would have a molecule. So here we go. When water dissolves an ionic structure, it rips it apart. So here we go. We have the same molarity. If that's the case, classify the substances. So that's going to be rule number 1. Are they, and as a general rule, ionics will change the BP and FP more. So we want to choose the ionic choice. Okay, so now take a look at the next example here. Okay, so when we take a look here, they're all solutions because they're AQ, and notice it's the same, they all have the same solute. So they all have the same solute, but they have different concentrations. So they have different concentrations. So I hope when you notice they go from 2.5, 1.5, and 0.5, that the answer that you eliminate right away is the 1.5 because it's in the middle. So which one is going to have the greatest impact on boiling point and freezing points? Well, it either has to be the one with the highest concentration or the one with the lower concentration, right? So here we go. The higher the concentration, the more cations and anions that are produced in solution. So if you have the same solute, different concentrations, choose the highest concentration. So your highest concentration value, because it has the most parts dissolved. So our best answer here would be A, highest concentration. Now, take a look here. In this next question, we are given no molarity values, and we have all different types of solutes. So here we have no molarity. And what we need to do first is classify. So if there's no molarity values, we have to start off with classifying the substances. So classify as ionic or molecular. So NaCl, metal, nonmetal. So I understand that that is ionic because I have a metal plus a nonmetal. C, H, and O, they're all nonmetals. So I understand that this is a molecule. And now my last one, magnesium, is a metal. Br is a nonmetal. So here I have a metal plus a nonmetal, so that this is ionic. As a general rule, an ionic will affect the BPs more than a molecular. So I'm going to lean towards the ionics. Okay, so that means B is not an answer. Because it is a molecule, when you dump this into water, water does not, it's a molecule. It's made up of atoms. There's no ions. So the water just pulls one molecule away from the other ones. And so we just end up with a structure that looks like this. So water, and when this is dissolved, it produces one particle per dissolved unit. Now, NaCl, it's ionic. It is a salt. So when you dump this into water, water rips the cation away from the anion. So in this case, the Na is ripped away from the Cl. So the cation is ripped away from the anion. So for every unit of NaCl that is dumped into water, it produces 2 parts. And when we take a look at this one, MgBr2, it is also ionic. So when water rips it apart, it rips the cation, Mg plus 2. And for every Mg cation that it pulls away from the crystal lattice, take a look. It pulls away, and I'm going to write it out this way, 2 different bromides. So for every particle of this particular salt that's ripped apart, there are 3 parts produced in solution. So what you need to do is take a look. Choose the one that produces the most parts. So most parts in solution. So our best answer here is C, because the magnesium bromide produces 3 parts in solution.